My name is Christian Boehm. I'm one of the co-founders of Mondaic. I'm joined here today by Chris Udell, who's the head of business development here at our company. Thanks also to Steve. It was actually a great prelude to our talk, because all of the topics that you mentioned about HDF5, how do we organize data, and in our particular case also, how do we do data fusion and bring together simulated data with measurements, and how do we organize that? That is also highly relevant to the work that we do. And without the next maybe 30 minutes or so, we'd like to give you a quick walkthrough of what we've been doing in terms of digital twins for ultrasonic simulations, and then also a novel method to image reconstruction with ultrasonic data. So we're going to split the talk between Chris and I, and just to quickly start off a little bit of background about who we are. We originally are a spin-off company from the University of ETH in Zurich, founded in 2018. Still a very small company, so we're currently a team of 11. And we focus really on exploring waves across all different spatial scales, from medical ultrasound all the way to global scale seismology. We have formed a strategic collaboration for subsurface imaging with Shearwater Geoservices, and generally we develop software for simulation and imaging. We do consulting, and we engage in joint R&D projects. Our clients range from industry, academia to governmental institutions. When you do software, it's actually fairly simple to go international. So although we're pretty small, we do have a fairly international user base. We're really proud to see our software being used all around the globe in millions of simulations. And there's also a very strong tie to R&D projects. So we do see quite a huge output of scientific publications of the use of our software. So what is it that we do? Well, just a quick gap in scales. Where we originally come from is what you can see here on the top row. And those are waves that are very different from ultrasonic waves. Those are seismic waves. So we have been working together with NASA in the context of their InSight mission to simulate Mars quakes, to then infer information about the interior structure of Mars. We have done quite a lot of work on simulating earthquakes and seismic hazard. We do have waves that still propagate over thousands of kilometers. They can be measured on land or in subsea with distributed acoustic sensing. And for subsurface imaging, this is probably the pillar that promoted this method the most over the last couple of decades. Many of the HOIS members, I think, are from the energy sector, and many of these companies have really driven the developments of waveform simulations and waveform inversions as a very powerful method to analyze the subsurface. This is primarily for resource exploration, but nowadays also shifted towards carbon sequestration, geothermal energy, and site characterization for wind farms. So here we see waves propagating over really long distances. And the question might be, what does it have to do with ultrasound and NDE? Well, the same physical principles, they can be transferred to much smaller scales. And this is now what we see at the bottom. Borehole acoustics, where we are much higher in frequencies and much shorter distances, but we see the same physical phenomena occurring. We have waves interacting with the material properties and the geometries of the objects. We have NDT inspections on potentially curved surfaces, like for pipelines. And if we even scale down the propagation distances smaller, we end up with medical ultrasound, where we see that nowadays scanning devices for ultrasonic breast cancer imaging have reached the precision of MRI. So there's really a lot that we can infer from ultrasonic measurements. And the same physical principles literally apply from 10,000s of kilometers if we study waves on Mars, all the way down to the millimeter scale that might be relevant for medical imaging. So what we're trying to do is we're trying to promote this method for ultrasonic NDE applications. I want to give you a little bit of background about our technology, and then finish up with a couple of case studies, and hopefully engage in a discussion of how this could be useful for the projects that you're working on. So I guess I don't need to tell you, ultrasound is a great modality to non-destructively analyze specimen. It's widely used. It's quite successful. You have conventional inspection techniques based on A scans, B scans, or C scans. We've heard a lot about this already in the previous talk. And this works great in many applications. However, we think that we don't really use the full potential of ultrasonic imaging yet. And this is when it comes to quite challenging testing environments, where the fact that all these scanning techniques only use partial data reaches its limit. It then leads to potentially low sensitivity and requires a lot of manual interpretation. And this is particularly the case when we have complex materials, for instance, inhibiting quite a strong anisotropy, or if we need to deal with quite complicated geometries, which are hard to represent in array-based approximation of ultrasound. So what we're trying to do is we're trying to transfer a technology that has been developed primarily in the geophysical sector of analyzing waves and inferring information about unknown objects from these waves. And this is what we call WSCAN, the waveform scan. It's a quantitative imaging method that try to infer three-dimensional models of the interior of an object through ultrasound tomography. And at its core, we do have a physics-informed digital twin, which really encapsulates all the waveform physics that are at play when we do an inspection. So here we have a simple example of a CFRP plate. And as you can see from a single piezo element, the wave field that is emitted becomes quite complex very quickly. We have a strong anisotropy that we see. We have interaction with a delamination that leads to multiple reverberations. We have backskirted waves. We have diode waves. So there's a lot of complexity at play that's typically not captured if we approximate the ultrasonic wave just by a simple array. By bringing in more accurate physics, we're then able to reconstruct high-resolution images, even though we're using low frequencies, and we can really turn ultrasonic inspection data into automated reports. How does this work? Well, in a nutshell, full waveform inversion tries to exploit a lot more data than conventional ultrasound. If we see a simple A scan depicted here, you all know that a time of flight inversion method would essentially time gate the first arrival. We would get a travel time, and from that we could essentially do a simple approximation. The time of flight is equal to distance divided by sound speed. So if we wanted to infer the material properties, we could easily solve for sound speed in this case. But what you can also see from this little chart here is there's a lot of data that we'll just throw away by just looking at the time of flight. And this is what waveform inversion is trying to do. It really tries to utilize all the data available and invert and reconstruct a three-dimensional model of the interior using those data. The tricky part is, in this situation, we don't have this simple relation between time of flight or the measurement and the material properties. So we don't really know how we can relate those data to the interior structure. And this is why we have to solve a computationally more complex problem in order to get to this point. But in a nutshell, what you can see on the right-hand side is why this method can be very powerful. We here have three different A scans overlaid to each other. And as you can see, the direct arrival doesn't really show any difference. There's only tiny differences maybe in the amplitude. But you can see for the later arrivals, you do see indeed quite some differences. And those are data taken from a block of concrete where we do have a healthy structure and once a structure with an air void in it, and once a structure with some water inclusions in the duct. And you can see that if we really analyze the long observations that we have here, differences appear, and we are trying to use those information to then reconstruct the interior structure with waveform inversion. So really trying to reverse engineer those signals, get a match to the actual data. By doing this iteratively, we then reconstruct a 3D model of the elastic properties. A great part of this is that all the invention and innovation really only happens on the data processing side. So we don't require any different hardware, or we do not need to acquire data in a different way. We can work with off-the-shelf conventional probes, so we can use phased array, we can use guided waves, acoustic emission, impact echo. That really doesn't matter that much. The only important point is we're really looking for applications where current ultrasound may not give you the quality or the results that you're expecting to get. To zoom in a little bit more, this is now a bit of a more technical slide of how the method works in principle. Is we always start from a digital twin. And digital twin obviously is a widely used buzzword. In our terminology, digital twin really means a model of the interior structure that we use to digitally represent ultrasonic wave propagation in this twin. So if we have this, we can start with a simulation. We can simulate the ultrasonic wave field as it would be emitted in an experiment, which gives us simulated data, which we can then compare to the measurements. And most of the time, we won't know the material properties of our object very well. This is the whole point of doing the inspection in the first place. So by comparing then simulated to measured data, we'll perform data fusion, and we will get a discrepancy between both. And this discrepancy is where the method can then extract sensitivities that will tell us how would I need to modify my digital twin in order to have a better match between the measurement and the simulated data. And by doing so in an iterative scheme, I can then improve my digital twin. I can keep iterating and refining my digital twin to eventually match the data that I have observed with my simulations. And by doing so, then creating an accurate representation of the interior properties of my specimen. So at the heart of it is really a digital twin, and we call it a physics-informed digital twin to distinguish it also a bit from a pure simulation tool. So we really want to perform data fusion, comparing simulated data to the measurements that we can take out of the field. And these physically accurate simulations can capture all the complexities that we've seen in the previous animation that are at play when we perform ultrasonic measurements on a complicated structure. This can include anisotropy, attenuation, multiple scattering, reflections. So it's really complicated wave field as the ones that you've seen in the animations previously that occurs after a short amount of time. And if we can capture this in the simulation, we might also then use all the data available for the image reconstruction techniques. Now you might say this all sounds great, but this is, we tried this before, and this is extremely costly. And this is really where cloud computing, GPUs, and tailored methods to simulating waveform propagation come into play. What we develop is not a multi-physics tool that can simulate all kinds of different physics. We solely focus on the wave equation, but we can solve that very, very efficiently and orders of magnitudes faster than conventional multi-physics tools. How is this helpful? Well, you can see a small example on the right-hand side of a block of concrete, where you can see at the very bottom now an animation going where the black line is a measurement that we took on this block, and the red line is the simulation that we do after calibration. And we can really see that the observed data and the simulated data match literally wiggle by wiggle over a very long measurement time. If we can reproduce an ultrasonic measurement that accurately in a digital twin, it really helps us to understand and characterize the signals. We can use that to optimize sensor positions. We can also create lots of synthetic scenarios that can help with validation of machine learning algorithms without the need of manufacturing a lot of specimens manually and doing measurements on these specimens. And then finally, we can also use it to estimate and quantify the probability of detection for any given application. So in a nutshell, what we do is we utilize cloud computing by sending data to the cloud and process it in the cloud in order to get reasonable time to solutions. And then we send back the data and the results to whoever is taking the measurements and allow them to analyze the results on site or later on in post-processing. This enables digital twin building, virtual prototyping, quantitative imaging, and monitoring. So really a lot of application that we're seeing coming up on the horizon where this can be useful. And again, ultrasound is widely used and is very powerful. If you have an application where ultrasound is already working well, we won't be able to do any better. So we're really focusing on inspection challenges where currently ultrasound struggles to give good results. So for instance, if the received signal is not well understood because we have a complex interaction with the material's interior structure, or the interpretation is very difficult, leading to many false calls. So here additional physics might help to better understand what I'm seeing in my images. Or when traditional simulation methods are either very expensive to carry out, or they just don't match reality because they simplify the physics that are at play. 3 examples that Chris will go into more details in some case studies are, for instance, guided waves, acoustic emission, or ultrasonic inspections of concrete. So I really see a lot of potential in this method, and to convince you that this is not just a pipe dream, but something that also works on real data, I'll hand over to Chris to walk you through some case studies.
Thanks, Christian. Yes, the first case study I'll go through is a guided wave in a composite panel with stringers. This is really to show you the process, and it's applicable to other types of materials, other types of ultrasound as well. The process is fairly similar between all of them as well. Composite panels were important as well, especially things like fiber waviness or delaminations out of plane, and that's why we've we've come quite far on this project, and this is a good one to show as well. So to start off the simulation, you do need a CAD model. Because WScan uses the spectrum element method, you also need to mesh that, but you don't need to worry about creating the mesh. This process is inside to do that for you. What you can mesh is things like solid fluid interfaces, so any kind of pipe filled with fluid or whatever. And also here what we've seen, this layered structures, and this is modeling the anisotropy in composite panels. The next question I'm usually asked is, well, Chris, I've got a CAD model, but actually that doesn't represent what's actually in real life, and that's quite correct. There are tolerances, especially with service inspections as well, where they could be, you've just got a simple drawing and the asset's over 50 years old. Yes, that will be difficult to get a match first time, but that's where our procedures help. We have shape optimizations throughout the inversions. But it's good to have a close CAD to start off with, and you'll see the examples what we do here as well. But yes, you don't need a fully accurate CAD to start off with, and then our software will correct the CAD, so then you have a better CAD model for the future as well, using the ultrasound that you're getting. So then we run a simulation, much like we know the equipment. What we're modeling here is a guided wave from a single piezo element propagating in this panel there. So you can see the anisotropy because it's not a full sphere, and you can also see some waves traveling down the stringer as well. Very light, but it's all there. So that's how the ultrasound travels through the panel in a simulated case. We'd then like to calibrate that. So what we have here is the simulated data on the left, and then we have access to a laser Doppler vibrometer to image the vibrations from that as well. This is actually the data from the LDV scan there as well. Again, you don't need exactly this equipment. It's just really this really shows the vibrations across the whole channel. So it's quite nice to tell for the to show you what we can do. And you can see already that the match is quite good. You've already got these bulk waves you can see down the stringer, and you've got the similar pattern. At least it looks close, but it's not a good fit. What we've used here is the material specs as defined by the OEM, and you can see the difference here. This is the piezo is here, and it's we've taken from that LDV scan a line down there. You can see this is reflections from the sidewall. The black data is the data from the LDV, and the red data is the simulated data, and you see there's not a great match there. But by calibrating now the entire elastic tensor, we can optimize the fit, and you can see now, at least at the first phase, we've got a very good match, even for off-plate shear moduli as well. So it shows that our simulation is sensitive to the elastic properties. So now we put that back in the model, and you can then, you see the, again, optimized simulation based on the real data. We've got some Teflon samples in this piece as well, and this is before we put it in, but it also shows defects very clearly. But what you can do is from that, because you've got from that whole panel there, you can actually take any point on that, and you can extract the Young's moduli and the thickness and other material properties as well. So it's not just a C-scan you're getting, it's a full material properties that you can extract from that single piezo transducer. So these are the types of parameters you can extract. Things like thickness, which is normal. You also can get out the material velocity, the P and the S wave, the density of the material, Young's modulus and shear modulus. If you're using guided waves, you can also calculate the dispersion curves, and even material properties like the case depth could also, because that would be a different velocity. So that was more of a production-based application. We do have also in-service inspection experience as well to show the practicality on aging assets. And this particular example is for concrete inspection. Again, it's applicable to other ones. And this is where we didn't really know the asset we're inspecting in full. You can see here, it's a retaining wall with ribs. And what the client here wanted to do was make a scan to find out where they could put additional anchor points in there as well. We didn't have a CAD model. We had this drawing, and I don't know how old it was, but that's all we had. And we took that as the initial model and then began a simulation in this digital twin. So this is using the ProSec Pundit, low frequency ultrasound tomography machine. And you can see this is how the ultrasound flows into this retaining wall and then the back ribs there as well. What we wanted to avoid is of course drilling when there's rebar underneath. So any kind of density anomalies is important to find. So using this iterative data fit, so it's not just one full wave inversion we run, it can be many, because the more iterations you run, the closer to reality you get. So you can see here, as we're running more and more iterations, the fit for the red to the black line is getting closer and closer. And we can do that because we're fast. As Christian mentioned before, compared to standard finite element models, we're about 1,000 times faster than that. So it means you can run more and more of those iterations to fit the data better. I think this one goes up to 10. Yes, 9. So yes, you can see the data fit slowly getting closer and closer to reality. So after 15 iterations of full wave inversion, you see you've got now a very good fit to the data. This is the data taken from the device, and now with the full wave inversion applied, you can see with a lot better resolution the actual structure in there as well. If you can make out as well here, when we look at the density anomalies, rebar or metal inclusions can be seen much clearer from the full wave inversion image rather than the raw data or process data. All right, and then back to Christian now, who will go about some more examples that we've run on assets that are probably a little bit closer to home.
Yeah, thanks, Chris. So yeah, the last couple of slides we want to go through. This is now probably a bit further away from real data applications, but something where we do see a lot of potential, and we are interested in your thoughts on where this could be applicable to the problems that you might be facing with tanks and pipes. So a study we carried out so far purely synthetically is on acoustic emission monitoring of storage tanks. And again, here the question is often, how do signals that I can observe with acoustic emission sensors on the sidewall of the tank really detect corrosion that might happen at the tank floor? There are complicated physics at play. We do have reflections and refractions of the wave. We do have a solid fluid interaction between the fluid-filled tank and the outer sidewalls. Same holds true for the bottom of the tank. And we do have a geometry which can be more complex. Here in the simulation, we only see a cylinder, but as you all know, the interior of such a tank can be quite complex, and the waves will interact with those geometries as well. Acoustic emission in itself is also a modality that is quite widely used for monitoring of concrete structures. So this is a project we're currently running on a bridge in Germany, where the idea is that acoustic emission can monitor the tension wire breaks. And if too many of these steel cables break, the bridge will eventually collapse. We want to prevent that. How can a simulation help in this case? Well, again, the digital twin can help with planning of such a monitoring system. We see an animation here where the key question was like, how should we place the acoustic emission sensors? How many of them would we need? And we can then hypothesize a potential event of a tension wire break and see how this would be observed in a virtual acoustic emission sensor that we can put into the simulation. We can also answer questions like, where do the waves actually propagate? Do they propagate along the metallic or steel tendon duct? Do they propagate mostly through concrete? You can see in those signals here here that there is a very early indication from a head wave that really travels through the steel and is then captured by the sensor. And then only later on, we see the majority of the signal that was propagating through concrete. When we turn to, again, a bit more complex geometries, this is, of course, an exaggerated example here. But if we look at pipelines and potential pipeline inspections, guided waves play a key role. Simulating them accurately can give us an idea of how the measurements would be sensitive to potential damages or thickness variations that we have. So here, for instance, we do have a thickness variation, which shows up as a density anomaly in our measurement. And what we can then see in the third panel is essentially the difference between two hypothetical measurements on a healthy pipe and on the damaged pipe with the anomaly in the wall thickness that we observe. So this is something we looked at into a little bit closer. How can this be used to thickness measurements using guided waves? So here we see a snapshot of the wave field, and in red colors, we have indicated the interaction of the wave field anomaly that comes from the interaction with a thickness variation that we might observe on the surface. So we do have a very small variation of thickness in the casing of the pipe, and we can see that there is indeed an imprint in the guided wave field that we simulate. And again, then by doing data fusion, by comparing measured data to simulated data, we hopefully can reconstruct the location of such a thickness variation in a pipe. Now, finally, just a few more applications that we've looked into, where we do think that understanding better the waveform physics of ultrasonic wave fields might give an advantage, and then could be interesting to exploit both for simulations, but also then for imaging applications. Where we do get quite significant interest is in modeling composite pressure vessels, GFRP pipes, tank floors as the one simulation we previously saw, potentially also for pigs on corroded surfaces in pipelines, estimating the fluid level or calcite at the bottom of pipelines. And then one example that you can see here on the right top is wind blade inspections. This is more similar to the example that Chris showed previously about laminate composites. So where there's a key interest in understanding or finding this bonds between the outer structure of the blade and the spar caps, and in general also composite sandwich structures where conventional ultrasound struggles because you can't really get in with high frequencies that you would need for high resolution. However, when we use guided waves, when we model more of the waveform physics, we can use much lower frequencies, and by doing so, we can also penetrate deeper structures better and get a better signal-to-noise ratio while not compromising the resolution we might obtain. So, coming to an end, we'd really like to open up for questions and then get your thoughts and input. So we develop software that has been used quite successfully in geophysical applications. We have done work on concrete inspections and composite materials as well. We don't think that that's the end yet, though. So we are really eager to learn about potential additional applications and problems that you might be struggling with when performing either ultrasonic measurements and trying to understand the signals. This would more be the digital twin part of it, or really want to improve on the inspections or the reconstruction of the 3D models that you might get from the interior. And a particular focus here would be in really getting a quantitative model of the material properties. So not just a grayscale image that indicates interfaces, but really getting a 3D map of what's my Young's modulus, what's my shear modulus inside of the structure. And with that, yeah, thanks so much for listening. Happy to take any questions. And looking forward to the discussion.
Yes, we will open the microphones so anyone can actually ask a question verbally. So simply put your hand up and we'll come to you, or alternatively just put some questions in the chat. First question I'd like to ask Ikesh to ask.
Thank you, Martin, and also thank you, Christian and Udell, for a very good overview. I see that in the previous slide you have mentioned it covers many different applications as well, not only the metallic component like piping, pipeline, and tanks, but also non-metallic GRP line as well you have mentioned. My question is, what kind of validation that you have carried out while developing this solution? Because I can understand that the propagation of guided wave and even acoustic emission signals that can vary a lot, depend on what kind of structure we are talking about. There is the impact of the material property as well, geometrical changes as well. So very much interested in knowing what kind of validation that you have carried out.
So I think the method itself is really widely applicable because we really include the geometric features and the different material properties in the digital twin, and by doing so we can simulate all kinds of waves. And this is, I think, what you saw in the slide at the very beginning, that our method has been used and validated from medical imaging applications all the way to Mars. So it is really working across a lot of different material properties and across a lot of different spatial scales. Where we've done the majority of work when it comes to NDE so far is in concrete, and particularly there the interest is the interaction of the concrete structure with or the ultrasonic waves with the concrete structure, and then tenon ducts that are there inside. So metallic tenon ducts with a particular question of how can we find void or water inclusions. That's one area where we've been quite active. The other one is mostly laminate composites made of carbon fiber. And here one of the key drivers is the strong anisotropy that we have in that material, which limits what you can do with conventional ultrasonic scanning techniques if you have waves propagating over longer distances. So we actually haven't done too much work on metal, and the primary reason being is that we have not come across a case where ultrasound is not already widely used and successful for instance finding thicknesses of a metal or finding cracks. So we're really looking for applications that are complex in terms of the waveform physics at play to provide benefit here.
Thank you, Udell. Clear?
I think regarding the validation as well that you've mentioned, it's kind of inbuilt into our process because you're calibrating against the real data. It's not just a simulation. It's using that real data and you reverse engineer that into, and that's kind of a validation process.
Yes, I think that's. I like the way that's the updating takes place, and it's similar to the sort of things you might find with sort of Bayesian statistics or neural networks and things like that, where you're continually updating models. But that's very impressive the way that happens. The quick question with some of the things you mentioned, like concrete or composites, as you say, those are, particularly in things like glass fiber composites, are materials that traditionally are very difficult to get ultrasound data from. What's the reason that you're so more successful with the W scan than you might be in using sort of conventional ultrasonics? So
for concrete, we are kind of right from the get-go quite limited on which frequencies we can use. And this is primarily because the grain size prevents us from using higher frequencies. And if we go to even lower frequencies, we don't have any resolution. So there, the application really determines what frequencies are kind of applicable. And then the problem is that the signals, they are really complicated because we do get a lot of reflections from the V-bar. We do get interaction with other structures like tenon ducts. We might have some complex geometries at play here. So this is where acquiring ultrasonic data for concrete seems to work pretty well. But analyzing those data is often hard. And this is just because you have so many effects that you can't really capture if you were to approximate the wave by just, a pulse you send in and an echo that you receive. If you model the entire wave field and really model also the interaction with the interior structure, you can make use of those data, and it's easier then to infer high resolution images. For composites, I think one of the key difference is that because we model more of the waveform physics, we typically do get higher resolution at lower frequencies. So in NDT, you would often say, well, if I want to have a certain sensitivity to a defect of a certain size, I need to go at least this high in frequency. Otherwise, I might be missing this structure. And this can be relaxed if you use, again, more of the wave field you exploit. You're trying to reverse engineer more of the signal that you record. And by doing so, you can get similar resolution at lower frequencies. And this is what then really opens up for the composite applications a very interesting avenue, because with the lower frequencies, you then do not struggle with attenuation that much, and you can really penetrate thicker composite materials or sandwich structures quite effectively, and then really apply ultrasound for the inspection of those materials.
I think I probably missed it out on my slide as well, is that the guided waves we were using were down at 100 kilohertz. We seem to be compatible with a 3.5 to 5 megahertz C-scan on terms of resolution, even though we're working at those frequencies. And you can actually see the difference in the thickness of the layers, even working at 100 kilohertz as well.
Yeah, that's very impressive. There's a couple of questions here on the chat. Roughly how long is the runtime of the current models?
Excellent question. I think this is also the primary reason why we have this talk today and not maybe 10, 15 years ago when people in geophysics were picking up that technology. So of course this is, in terms of data processing, more expensive than a simple C-scan projection. With GPUs and with cloud computing, we can bring those compute times down. It is still not a method that will work in situ, and it is a long way out to actually work that fast. However, for the examples that you saw, for instance, the concrete inspection data, this runs without heavy compute machinery, i.e. a workstation is completely enough, in about 15 to 20 minutes to get this reconstruction. So compute time and time solution is still a limiting factor. We know and understand, but I think we're doing our homework to make this faster, and yeah, GPUs and then the cloud also really helps to make this feasible and viable for more applications.
Yes, certainly you seem to be dealing with some of the more challenging things from an inspection standpoint, where ultrasonics does have problems. So that was impressive to see. A question here from Sean Keir. What are the primary differences between your approach and other simulation tools like SIVA?
So SIVA primarily focuses on simplified waveform physics. They do also have the tools to really simulate the entire kind of space-time cylinder of the wave field. However, as far as I know, this mostly works in 2D, and I think the 3D capabilities are limited. And I think that the big difference is that when we really want to simulate the entire high-fidelity wave field, our approach is very fast, and this is because we do discretize the wave equation with a method that's called the spectral element method, which is tailored and designed to waveform physics, and it's not comparable to a kind of conventional finite element method. I guess SIVA is an extremely powerful and widely used tool. I've seen it primarily being used for using approximations of the wave equation, and I think this is where it's super strong. When it comes to really simulating, let's say an elastic wave in full anisotropy, this is where the discretization that used, which again is inspired from methods in geophysics, where this becomes really, really fast.
Couple of quick questions. One was in relation to you mentioned the use subsea of the waves. Does it give you information, as well as on the seabed and structure, does it give you information on the seabed infrastructure in terms of subsea modules, pipelines, that type of equipment, and what sort of information would you get?
Subsea, well, in general, I think it is always the interplay between data quality, of course, and then which frequencies to use, which then inform us about the resolution we would obtain. So if we look at subsea imaging, especially with distributed acoustic sensing recordings, so far we've primarily used that information for subsurface imaging, where we do have much longer structure, and then any kind of pipeline is out of scope because the spatial extent would be way too small. That being said, it is it is always that trade-off and interplay between what are the frequencies that I'm using to then allow me to infer also smaller material properties. But subsea, we do have some clients using it to also infer elements in the water column. But I think the primary application is really looking to the subsurface and what's going on there.